Sodium. Sodium is a chemical element with symbol Na and atomic number 11. It is a soft, silvery white, highly reactive metal. Sodium is an alkali metal, being in group 1 of the periodic table, because it has a single electron in its outer shell that it readily donates, creating a positively charged ion, the Na and cation. Its only stable isotope is 2,3Na. The free metal does not occur in nature, and must be prepared from compounds. Sodium is the 6th most abundant element in the Earth's crust and exists in numerous minerals such as feldspars, sodalite, and rock salt. Many salts of sodium are highly water-soluble. Sodium ions have been leached by the action of water from the Earth's minerals over eons, and thus sodium and chlorine are the most common dissolved elements by weight in the oceans. Sodium was first isolated by Humphrey Davy in 1807 by the electrolysis of sodium hydroxide. Among many other useful sodium compounds, sodium hydroxide is used in soap manufacture, and sodium chloride is a de-icing agent and a nutrient for animals including humans. Sodium is an essential element for all animals and some plants. Sodium ions are the major cation in the extracellular fluid and as such are the major contributor to the ECF osmotic pressure and ECF compartment volume. Loss of water from the ECF compartment increases the sodium concentration, a condition called hypernatremia. Isotonic loss of water and sodium from the ECF compartment decreases the size of that compartment in a condition called ECF hypovolemia. By means of the sodium-potassium pump, living human cells pump 3 sodium ions out of the cell in exchange for 2 potassium ions pumped in, comparing ion concentrations across the cell membrane. Inside to outside, potassium measures about 40:1, and sodium, about 110. In nerve cells, the electrical charge across the cell membrane enables transmission of the nerve impulse and action potential when the charge is dissipated. Sodium plays a key role in that activity. Sodium at standard temperature and pressure is a soft silvery metal that combines with oxygen in the air and forms grayish-white sodium oxide unless immersed in oil or inert gas, which are the conditions it is usually stored in. Sodium metal can be easily cut with a knife and is a good conductor of electricity and heat because it has only one electron in its valence shell, resulting in weak metallic bonding and free electrons, which carry energy. Due to having low atomic mass and large atomic radius, sodium is third least dense of all elemental metals and is one of only 3 metals that can float on water, the other 2 being lithium and potassium. The melting and boiling points of sodium are lower than those of lithium but higher than those of the heavier alkali metals potassium, rubidium, and cesium, following periodic trends down the group. These properties change dramatically at elevated pressures. At 1.5 bar, the color changes from silvery metallic to black. At 1.9 bar the material becomes transparent with a red color, and at 3 bar, sodium is a clear and transparent solid. All of these high-pressure allotropes are insulators and electrides. In a flame test, sodium and its compounds glow yellow because the excited 3s electrons of sodium emit a photon when they fall from 3p to 3s. The wavelength of this photon corresponds to the D line at about 589.3 nm. Spin-orbit interactions involving the electron in the 3p orbital split the D line into 2 at 589.0 and 589.6 nm. Hyperfine structures involving both orbitals cause many more lines. 20 isotopes of sodium are known, but only 2,3Na is stable. 2,3Na is created in the carbon-burning process in stars by fusing 2 carbon atoms together. This requires temperatures above 600 megakelvins in a star of at least 3 solar masses. 2 radioactive, cosmogenic isotopes are the byproduct of cosmic ray spallation. 2,2Na has a half-life of 2.6 years and 2,4Na, a half-life of 15 hours. All other isotopes have a half-life of less than 1 minute. 2 nuclear isomers have been discovered, the longer-lived one being 2,4MNA with a half-life of around 20.2 milliseconds. Acute neutron radiation, as from a nuclear criticality accident, converts some of the stable 2,3Na in human blood to 2,4Na. The neutron radiation dosage of a victim can be calculated by measuring the concentration of 2,4Na relative to 2,3Na. Sodium atoms have 11 electrons, one more than the extremely stable configuration of the noble gas neon. Because of this and its low first ionization energy of 495.8 kJ/mol, the sodium atom is much more likely to lose the last electron and acquire a positive charge than to gain one and acquire a negative charge. This process requires so little energy that sodium is readily oxidized by giving up its 11th electron. In contrast, the second ionization energy is very high, because the 10th electron is closer to the nucleus than the 11th electron. As a result, sodium usually forms ionic compounds involving the Na and cation. The most common oxidation state for sodium is +1. It is generally less reactive than potassium and more reactive than lithium. Sodium metal is highly reducing, with the standard reduction potential for the Na+/Na couple being 2.71 volts, though potassium and lithium have even more negative potentials. Sodium compounds are of immense commercial importance, being particularly central to industries producing glass, paper, soap, and textiles. The most important sodium compounds are table salt, soda ash, baking soda, caustic soda, sodium nitrate, D, and trisodium phosphates, sodium thiosulfate, and borax. In compounds, sodium is usually ionically bonded to water and anions and is viewed as a hard Lewis acid. Most soaps are sodium salts of fatty acids. Sodium soaps have a higher melting temperature than potassium soaps. Like all the alkali metals, sodium reacts exothermically with water, and sufficiently large pieces melt to a sphere and may explode. The reaction produces caustic soda and flammable hydrogen gas. When burned in air, it forms primarily sodium peroxide with some sodium oxide. Sodium tends to form water-soluble compounds, such as halides, sulfates, nitrates, carboxylates and carbonates. The main aqueous species are the aquo complexes plus, where N equals 4,8, with N equals 6 indicated from X-ray diffraction data and computer simulations. Direct precipitation of sodium salts from aqueous solutions is rare because sodium salts typically have a high affinity for water, an exception is sodium bismuthate. Because of this, sodium salts are usually isolated as solids by evaporation or by precipitation with an organic solvent, such as ethanol. For example, only 0.35 g/L of sodium chloride will dissolve in ethanol. Crown ethers, like 15-crown-5, may be used as a phase transfer catalyst. Sodium content in bulk may be determined by treating with a large excess of uranyl zinc acetate, the hexahydrate 2-ZNNA6H2O precipitates, and can be weighed. Cesium and rubidium do not interfere with this reaction, but potassium and lithium do. Lower concentrations of sodium may be determined by atomic absorption spectrophotometry or by potentiometry using ion-selective electrodes. Like the other alkali metals, sodium dissolves in ammonia and some amines to give deeply colored solutions. Evaporation of these solutions leaves a shiny film of metallic sodium. The solutions contain the coordination complex 6+, with the positive charge counterbalanced by electrons as anions. Cryptands permit the isolation of these complexes as crystalline solids. Sodium forms complexes with crown ethers, cryptands and other ligands. For example, 15-crown-5 has a high affinity for sodium because the cavity size of 15-crown-5 is 1.72.2 A, which is enough to fit sodium ion. Cryptands, like crown ethers and other ionophores, also have a high affinity for the sodium ion. Derivatives of the alkalide Na are obtainable by the addition of cryptands to solutions of sodium in ammonia via disproportionation. Many organosodium compounds have been prepared. Because of the high polarity of the CNA bonds, they behave like sources of carb anions. Some well-known derivatives include sodium cyclopentadienide and trityl sodium 3-CNA. Because of the large size and very low polarizing power of the Na and cation, it can stabilize large, aromatic, polarizable radical anions, such as in sodium naphthalenide, Na+, a strong reducing agent. Sodium forms alloys with many metals, such as potassium, calcium, lead, and the group 11 and 12 elements. Sodium and potassium form KNA2 and NaK. NaK is 40–90% potassium and it is liquid at ambient temperature. It is an excellent thermal and electrical conductor. Sodium-calcium alloys are byproducts of the electrolytic production of sodium from a binary salt mixture of NaCl-CaCl2 and ternary mixture NaCl-CaCl2-BaCl2. Calcium is only partially miscible with sodium. In a liquid state, sodium is completely miscible with lead. There are several methods to make sodium-lead alloys. One is to melt them together and another is to deposit sodium electrolytically on molten lead cathodes. NaPb3, NaPb, Na9Pb4, Na5Pb2, and Na15Pb4 are some of the known sodium lead alloys. Sodium also forms alloys with gold and silver. Group 12 metals are known to make alloys with sodium. NaZn13 and NaCd2 are alloys of zinc and cadmium. Sodium and mercury form NaHg, NaHg4, NaHg2, Na3Hg2, and Na3Hg. Because of its importance in human metabolism, salt has long been an important commodity, as shown by the English word salary, which derives from salarium, the wafers of salt sometimes given to Roman soldiers along with their other wages. In medieval Europe, a compound of sodium with the Latin name of sodinum was used as a headache remedy. The name sodium is thought to originate from the Arabic suda, meaning headache, as the headache alleviating properties of sodium carbonate or soda were well known in early times. Although sodium, sometimes called soda, had long been recognized in compounds, the metal itself was not isolated until 1807 by Sir Humphry Davy through the electrolysis of sodium hydroxide. In 1809, the German physicist and chemist Ludwig Wilhelm Gilbert proposed the names natrinium for Humphry Davy's sodium and kalium for Davy's potassium. The chemical abbreviation for sodium was first published in 1814 by Johannes Jacob Berzelius in his System of Atomic Symbols, and is an abbreviation of the element's new Latin name natrium, which refers to the Egyptian natron, a natural mineral salt mainly consisting of hydrated sodium carbonate. Natron historically had several important industrial and household uses, later eclipsed by other sodium compounds. Sodium imparts an intense yellow color to flames. As early as 1860, Kirchhoff and Bunsen noted the high sensitivity of a sodium flame test, and stated in Annalander Physik und Chemie. In a corner of our 60m3 room farthest away from the apparatus, we exploded 3 mg of sodium chlorate with milk sugar while observing the non-luminous flame before the slit. After a while, it glowed a bright yellow and showed a strong sodium line that disappeared only after 10 minutes. From the weight of the sodium salt and the volume of air in the room, we easily calculate that 1 part by weight of air could not contain more than 1/20th millionth weight of sodium. The Earth's crust contains 2.27% sodium, making it the 7th most abundant element on Earth and the 5th most abundant metal, behind aluminium, iron, calcium, and magnesium and ahead of potassium. Sodium's estimated oceanic abundance is 1.08 times 104 mg per liter. Because of its high reactivity, it is never found as a pure element. It is found in many different minerals, some very soluble, such as halite and natron, others much less soluble, such as amphibole and zeolite. The insolubility of certain sodium minerals such as cryolite and feldspar arises from their polymeric anions, which in the case of feldspar is a polysilicate. Atomic sodium has a very strong spectral line in the yellow-orange part of the spectrum. This appears as an absorption line in many types of stars, including the Sunday. The line was first studied in 1814 by Joseph von Fraunhofer during his investigation of the lines in the solar spectrum, now known as the Fraunhofer lines. Fraunhofer named it the D line, although it is now known to actually be a group of closely spaced lines split by a fine and hyperfine structure. The strength of the D line means it has been detected in many other astronomical environments. In stars, it is seen in any whose surfaces are cool enough for sodium to exist in atomic form. This corresponds to stars of roughly F-type and cooler. Many other stars appear to have a sodium absorption line, but this is actually caused by gas in the foreground interstellar medium. The two can be distinguished via high-resolution spectroscopy, because interstellar lines are much narrower than those broadened by stellar rotation. Sodium has also been detected in numerous solar system environments, including Mercury's atmosphere, the exosphere of the Moon, and numerous other bodies. Some comets have a sodium tail, which was first detected in observations of comet Hale-Bopp in 1997. Sodium has even been detected in the atmospheres of some extrasolar planets via transit spectroscopy. Employed only in rather specialized applications, only about 100,000 tons of metallic sodium are produced annually. Metallic sodium was first produced commercially in the late 19th century by carbothermal reduction of sodium carbonate at 1100 degrees C, as the first step of the Deville process for the production of aluminium. The high demand for aluminium created the need for the production of sodium. The introduction of the Hall-Héroult process for the production of aluminium by electrolyzing a molten salt bath ended the need for large quantities of sodium. A related process based on the reduction of sodium hydroxide was developed in 1886. Sodium is now produced commercially through the electrolysis of molten sodium chloride, based on a process patented in 1924. This is done in a down cell in which the NaCl is mixed with calcium chloride to lower the melting point below 700 degrees C. As calcium is less electropositive than sodium, no calcium will be deposited at the cathode. This method is less expensive than the previous Castner process. The market for sodium is volatile due to the difficulty in its storage and shipping. It must be stored under a dry inert gas atmosphere or anhydrous mineral oil to prevent the formation of a surface layer of sodium oxide or sodium superoxide. Though metallic sodium has some important uses, the major applications for sodium use compounds. Millions of tons of sodium chloride, hydroxide, and carbonate are produced annually. Sodium chloride is extensively used for anti-icing and de-icing and as a preservative. Examples of the uses of sodium bicarbonate include baking, as a raising agent, and soda blasting. Along with potassium, many important medicines have sodium added to improve their bioavailability. Though potassium is the better ion in most cases, sodium is chosen for its lower price and atomic weight. Sodium hydride is used as a base for various reactions in organic chemistry, and as a reducing agent in inorganic chemistry. Metallic sodium is used mainly for the production of sodium borohydride, sodium azide, indigo, and triphenylphosphine. A once common use was the making of tetraethyl lead and titanium metal. Because of the move away from TEL and new titanium production methods, the production of sodium declined after 1970. Sodium is also used as an alloying metal, an anti-scaling agent, and as a reducing agent for metals when other materials are ineffective. Note the free element is not used as a scaling agent. Ions in the water are exchanged for sodium ions. Sodium plasma lamps are often used for street lighting in cities, shedding light that ranges from yellow-orange to peach as the pressure increases. By itself or with potassium, sodium is a desiccant. It gives an intense blue coloration with benzophenone when the desiccate is dry. In organic synthesis, sodium is used in various reactions such as the Birch reduction, and the sodium fusion test is conducted to qualitatively analyze compounds. Sodium reacts with alcohol and gives alkoxides, and when sodium is dissolved in ammonia solution, it can be used to reduce alkynes to transalkenes. Lasers emitting light at the sodium D line are used to create artificial laser guide stars that assist in the adaptive optics for land-based visible light telescopes. Liquid sodium is used as a heat transfer fluid in some types of nuclear reactors because it has the high thermal conductivity and low neutron absorption cross-section required to achieve a high neutron flux in the reactor. The high boiling point of sodium allows the reactor to operate at ambient pressure, but the drawbacks include its opacity, which hinders visual maintenance, and its explosive properties. Radioactive sodium-24 may be produced by neutron bombardment during operation, posing a slight radiation hazard. The radioactivity stops within a few days after removal from the reactor. If a reactor needs to be shut down frequently, NaK is used. Because NaK is a liquid at room temperature, the coolant does not solidify in the pipes. In this case, the pyrophoricity of potassium requires extra precautions to prevent and detect leaks. Another heat transfer application is poppet valves in high-performance internal combustion engines. The valve stems are partially filled with sodium and work as a heat pipe to cool the valves. In humans, sodium is an essential mineral that regulates blood volume, blood pressure, osmotic equilibrium, and pH. The minimum physiological requirement for sodium is 500 mg per day. Sodium chloride is the principal source of sodium in the diet, and is used as seasoning and preservative in such commodities as pickled preserves and jerky. For Americans, most sodium chloride comes from processed foods. Other sources of sodium are its natural occurrence in food and such food additives as monosodium glutamate, sodium nitrite, sodium saccharin, baking soda, and sodium benzoate. The U.S. Institute of Medicine set its tolerable upper intake level for sodium at 2.3 grams per day, but the average person in the United States consumes 3.4 grams per day. Studies have found that lowering sodium intake by 2 g per day tends to lower systolic blood pressure by about 2 to 4 mmHg. It has been estimated that such a decrease in sodium intake would lead to between 9 and 17% fewer cases of hypertension. Hypertension causes 7.6 million premature deaths worldwide each year. The American Heart Association recommends no more than 1.5 g of sodium per day. One study found that people with or without hypertension who excreted less than 3 grams of sodium per day in their urine had a higher risk of death, stroke, or heart attack than those excreting 4 to 5 grams per day. Levels of 7 g per day or more in people with hypertension were associated with higher mortality and cardiovascular events, but this was not found to be true for people without hypertension. The US FDA states that adults with hypertension and pre-hypertension should reduce daily intake to 1.5 g. The renin-angiotensin system regulates the amount of fluid and sodium concentration in the body. Reduction of blood pressure and sodium concentration in the kidney result in the production of renin, which in turn produces aldosterone and angiotensin, retaining sodium in the urine. When the concentration of sodium increases, the production of renin decreases, and the sodium concentration returns to normal. The sodium ion is an important electrolyte in neuron function, and in osmoregulation between cells and the extracellular fluid. This is accomplished in all animals by Na+/K+ ADPase, an active transporter pumping ions against the gradient, and sodium/potassium channels. Sodium is the most prevalent metallic ion in extracellular fluid. Unusually low or high sodium levels in humans are recognized in medicine as hyponatremia and hypernatremia. These conditions may be caused by genetic factors, aging, or prolonged vomiting or diarrhea. In C4 plants, sodium is a micronutrient that aids metabolism, specifically in regeneration of phosphenol pyruvate and synthesis of chlorophyll. In others, it substitutes for potassium in several roles, such as maintaining turgor pressure and aiding in the opening and closing of stomata. Excess sodium in the soil can limit the uptake of water by decreasing the water potential, which may result in plant wilting. Excess concentrations in the cytoplasm can lead to enzyme inhibition, which in turn causes necrosis and chlorosis. In response, some plants have developed mechanisms to limit sodium uptake in the roots, to store it in cell vacuoles, and restrict salt transport from roots to leaves. Excess sodium may also be stored in old plant tissue, limiting the damage to new growth. Halophytes have adapted to be able to flourish in sodium-rich environments. Sodium forms flammable hydrogen and caustic sodium hydroxide on contact with water. Ingestion and contact with moisture on skin, eyes, or mucous membranes can cause severe burns. Sodium spontaneously explodes in the presence of water due to the formation of hydrogen and sodium hydroxide. However, sodium exposed to air and ignited or reaching autoignition displays a relatively mild fire. In the case of massive pieces of sodium, the reaction with oxygen eventually becomes slow due to formation of a protective layer. Fire extinguishers based on water accelerate sodium fires. Those based on carbon dioxide and bromochlorodiafluoromethane should not be used on sodium fire. Metal fires are Class D, but not all Class D extinguishers are workable with sodium. An effective extinguishing agent for sodium fires is MEtLX. Other effective agents include Lithx, which has graphite powder and an organophosphate flame retardant, and dry sand. Sodium fires are prevented in nuclear reactors by isolating sodium from oxygen by surrounding sodium pipes with inert gas. Pool-type sodium fires are prevented using different design measures called catch-pan systems. They collect leaking sodium into a leak recovery tank where it is isolated from oxygen.